Hi. In this video, we are going to look at the topic of indeterminate equations. Sometimes they're called Diophantine equations. But before we go to that, we will also look at a few problems that will help you revise the concepts that we discussed in the previous number theory video, which was basically on congruences. So let's start with a few problems first, and then we'll move on to the topic of Diophantine equations. So the first question is this one. Prove that perfect squares perfect squares are congruent to either 0 or 1 modulo 4. Very simple question. We want to show that all perfect squares x square will be either 0 mod 4, 0 or 1 mod 4. Now, the question can be done very easily if you think of x as an integer and think of classifying those integers using modulo 2. So x mod 2 will either be an even number or an odd number, right? So it will either be 1 mod 2 or 0 mod 2. So that is the complete residue system for modulo 2, right? Either 0 or 1. These are the possible remainders. So in this case, it is an odd number and the number can be written as 2k plus 1. And in this case, it's an even number, so you can write it as 2k. So for any x, these are the two ways in which you can express those numbers. So obviously, when you do x square, you will get, if it is an even number, x is even, then you get 4k square, which is 0 mod 4, since it is clearly divisible by 4. And if you take the odd case, you will get 4k square plus 4k plus 1, which is basically 4 times k square plus k plus 1, which is obviously 1 mod 4. So what we are seeing is all integers will fall under either even or odd classes. And in both of these cases, you are getting the x square will only be 0 mod 4 or 1 mod 4. So that just tells us that any perfect square will always be either 0 or 1 modulo 4, right? Okay. Let's look at the next problem. This is question number 2. Here we have, let a and b be integers. P is a prime. P is a prime. And a power p is congruent to b power p mod p. We have to prove that a power p is congruent to b power p mod p square as well. So we are given that a power p is congruent to b power p mod p, but we have to prove this congruence. A power p is congruent to b power p mod p square, right? A and b are any integers, p is a prime. So now using Fermat's little theorem, we know that a power p is congruent to a mod p. Because you know Fermat's little theorem says a power p minus 1 is congruent to 1 mod p, right? So if you multiply both sides by a, you will get this, right? So we also know that b power p is congruent to b mod p. We are applying Fermat's theorem to both of these cases. So this implies that a mod p is congruent to b mod p, or a is congruent to b mod p, right? Because we know that a power p and b power p are congruent, so a and b must be congruent mod p, right? So this is a conclusion that we get from Fermat's theorem here. So that means that a can be written as p times some integer plus b, right? Because b is the remainder when you divide a with p. Here m is any integer. M is any integer. So now let's use this notation to try to prove this statement, right? We have to think of what is a power p. So a power p will be basically b plus m times p power p. And if you use binomial theorem here, it will be b power p plus pc1 b power p minus 1 mp. Correct. Plus so on, higher powers, and you get pcp mp to the power p, right? So now you can see here that from the third term onwards, the power of p will be mp square, mp cube, and so on, right? So all these terms are divisible by p square, are divisible by p square. So therefore, what we need to figure out is this term. These are the two terms that we need to worry about. Now, since we already know that a power p is congruent to b power p mod p, we already know this. This was given in the statement of the problem. So what we get basically, think about this term, second term. The second term is p times mp into b power p minus 1. So actually you notice that b times mp square b power p minus 1, this is it. So actually the second term is also divisible by p, right? The second term is also divisible by p square. My mistake. You already get this term is divisible by p square, right? So everything from the second term onwards is divisible by p square, right? And the only difference is in the first term. So you have a power p and b power p. A power p is equal to b power p plus these terms, which are divisible by p square, right? Now, from here, it follows that this is 0 mod p square, right? Since these second term onwards, everything is divisible by p square, it must be 0 mod p square. So that means if you take mod p square on both sides in this equation, it is guaranteed that a power p is congruent to b power p mod p square. Why is it guaranteed? Because you have an equality and these terms are anyway divisible by p square, so they will give 0 mod p square if you take mod on both sides. So you'll get a power p mod p square should be equal to b power p mod p square. Or you can say it in a different way by saying a power p minus b power p is divisible by p square, right? Which means that a power p and b power p are congruent to each other modulo p square. That is the proof of the theorem. We used basically binomial theorem to prove it, right? Okay, let's look at the next problem. This is question 3. Let A and M be coprime numbers, so their GCD is 1. Then there exists an integer k with 1 is less than equal to k is less than equal to m, such that a power k is congruent to 1 mod m. We have to show this, correct? So think about it. We have, because a and m are co-prime to each other, the m integers from a square till a power m are all co-prime with m, right? So if you divide all of these integers by m, their remainders, these are m integers if you divide them by m, then their remainders should form a complete residue system, 0, 1, 2, till m minus 1. If you take, excuse me, if you take any m integers which are all co-prime with m, then those m integers will definitely form a complete residue system with m, right? Why? For example, let's take three integers which are co-prime with 3, right? So we can construct 2, 2 square, 2 cube. All of these three integers are co-prime with 3. Now, what is the residue system that we get from these three integers? I'm just picking m is 3 and a is 2, which satisfies the condition. Now, think of the residue system here. It is 2 and 4 is 1 mod 3 and 8 is basically again 2 mod 3, right? Correct. So you're getting 1 and 2, right? You're not getting the 0. Correct. So here we are saying that these are m integers. You are getting the two possibilities that are other than 0. You're getting the other two possibilities here, right? So you're getting 1, 2, till m minus 1. So the idea is that this forms a complete residue system here. Once you have a complete residue system, what you can say is there must exist ij where 1 is less than I, less than j, less than equal to m, satisfying a power I is equal to a power j mod m. Why? Because there are m minus 1 possible ij's and there are m possible remainders. So you're basically applying pigeonhole principle. So you're saying that the number of numbers here ij will be m minus 1 and the number of remainders are m. So two of them will have the same remainder. So you will say that ai must be equal to a power I must be equal to a power j mod m, and because a power I GCD with m is equal to 1, you can rewrite this as a power I a power j minus I minus 1 equal to 0 mod m, congruent to 0 mod m, and therefore since a power I and m are co-prime, m must divide a power j minus I minus 1. So that this tells us that if you take j minus I as k, there must be a case such that a power k is congruent to 1 mod m. You have to apply pigeonhole principle and think of this set of complete residues. There will be two terms there which will have same remainder with m. So once you establish that, so for example, if you notice when we took 2 and 3, right, you got 3 when a was 2 and m was 3. If you took 3 powers like this, 2, 2 square, 2 cube, right? 3 integers like this. Notice that 2 and 8 were the two integers that were having the same residue when you took mod 3, right? 2 and 8 are both 2 mod 3. So similarly here also you will get a power I and a power j will have the same residue mod m, right? So there must be then, if you simplify this, you can say a power I minus a power j is 0 mod m, and then you take basically a power I common and you'll get a power j minus I minus 1. It must be 0 mod m, and we know that m does not divide a power I. So m must divide this. If m divides this, then there is some term a power j minus I which is 1 mod m. Which was which one? Which was 4. So the example using 2 and 3, we are getting the proof. Similarly, you could take another example. A and m is 1. Let's take a as 5, m as 7. And let's think of the set 5, 5 power 1, 5 power 2 till 5 power 7, right? You will be able to show that there must be at least two integers here such that 5 power j minus 5 power I will be congruent to each other, 0 mod 7. Why? Because you have 7 of these powers, right? The remainders are from 0, 1, 2 till 6. 0, 1, 2 till 6. But actually, 0 is not there in any of these, right? So here, if you think about it, I have made a mistake here. I should not have written 5 power 1 here. So it starts off with 5 power 1 and 5 power 2. So if you think of this set, there are 7 integers here, and there are only 6 possible remainders. No, why are there only 6 possible remainders? The idea is that 5 and 7 are co-prime with each other. So 5 power 1, 5 power 2, all of these numbers will also be co-prime with 7. Are also co-prime with 7. So 0 is not a possible remainder, right? So notice that 1, 2, 6, there are 6 possible remainders, but there are 7 numbers. 7 numbers, 6 remainders. So by pigeonhole principle, there are 2 numbers with the same remainder, right? If you call them 5 power j and 5 power I, we can say 5 power j minus 5 power I is 0 mod m, 0 mod 7. And as soon as you do that, you can say 5 power I, 5 power j minus I minus 1 is congruent to 0 mod 7. And now this means that this number is divisible by 7, but 5 power I cannot be divisible by 7. So this must be divisible by 7, which means 5 power j minus I minus 1 is 0 mod 7, which means there must be some 5 power j minus I, which is 1 mod 7. Right? So that is the logic. So I hope you have got the logic of the proof. It uses pigeonhole principle and the fact that there are only 6 possible remainders here, or m minus 1 possible remainders and m numbers. So 2 of the numbers have to have the same remainder. Okay. The next one is this question. Suppose p is greater than equal to 5. P is greater than equal to 5 is a prime. For p does not divide k, we define 1 by k or inverse of k as a solution of x satisfying the equation kx is congruent to 1 mod p. Okay. And now what we have to show here, prove that 1 by 1 square plus 1 by 2 square plus 1 by p minus 1 whole square is congruent to 0 mod p. Okay. So that is the question. Now think about it. Since p is prime, all the numbers less than p are co-prime with p, right? So 1, 2 till p minus 1. All of these numbers will compose a reduced residue system modulo p. Reduced residue system modulo p. Why? Because how many how many numbers are there which are co-prime to a prime? Phi of p is p minus 1. So these are the p minus 1 numbers that can constitute a reduced residue system modulo p. Now, there is a property of reduced residue systems that if you take these and if you take their inverses, these will also constitute a reduced residue system. If this is a reduced residue system, then their inverses also constitute a reduced residue system modulo p. Now, if I know this, that 1 by 1, 1 by 2, 1 by p minus 1 forms a reduced residue system, then we can say, so for p greater than or equal to 5, we can try to do the summation of k goes from 1 to p minus 1, 1 by k whole square. So that is basically correct. 1 by k whole square we are trying to do. Now 1 by k whole square is congruent to 1 by k square mod p, where k goes from 1 to p minus 1. Okay. And okay, so we probably need to do a slightly different approach here. Hmm. Yeah, I'll have to think about this one. We'll just park this for now, and we'll move on to the next topic. I'll have to think about this question a little bit. I'm not sure right now whether what I'm thinking is accurate or not. So for now, I'll continue with the lesson plan, which is we wanted to start Diophantine equations. So we'll look at these equations first right now. The question we'll address at a later stage. This is Diophantine equations. Basically, these are the kind of equations which are known as indeterminate equations. Why are they indeterminate? Because usually what they have is they have fewer equations and more unknowns. Fewer equations and more unknowns. So generally you solve them by using properties of number theory that you know. So first what we look at is we look at a few questions through which we'll learn 2-3 different methods. So the first method is the factorization method. Factorization method. The second method is congruence method. And finally, there is the inequality estimation or estimation method. So I will show you examples of how you use each of these methods to solve problems of Diophantine equations. So let's get started with this one. We have to prove that the equation x into x plus 1 plus 1 equal to y square has no positive integer solutions. Has no positive integer solutions. So let's approach this method by the factorization technique. So what we will do here is multiply both sides by 4. Multiply by 4 on both sides. So you will get 4x into x plus 1 plus 1 is equal to 4y square, which becomes 4x square plus 4x plus 1 equal to 4y square. And now, what is the benefit of doing that? We can write this as a perfect square. We can write this as 2x plus 1 whole square. But for that, we needed a plus 4, but we have only a plus 1. So it can be written as 1 can be written as 4 minus 3, right? So, right. So you will get, okay, I have made a mistake here. When you multiply by 4, it will become a plus 4 anyway. This is becoming a plus 4. And I need a plus 1 here. So this is 2x plus 1 whole square plus 3, right? Is equal to 4y square. Think about it. If you multiply by 4, you have a 4 already. So you have 4x square plus 4x plus 4. I'm using only 1 here, and I'm using a plus 3 like this. So what this does is it helps us set it up like this. 4y square minus 2x plus 1 whole square is equal to 3. And now this can be factorized, and this can be written as 2y plus 2x plus 1 multiplied by 2y minus 2x minus 1 equal to 3. So we have achieved the factorization that we wanted. Now the question was saying that we have to prove that there are no positive integer solutions. We'll try to prove by contradiction. We'll assume that this equation has positive integer solutions for x and y. If you assume this, then obviously 2y plus 2x plus 1 is greater than 2y minus 2x minus 1 if x and y are both positive integers. And since 3 is a prime, the only way 3 can be written as a product of two positive integers is 1 into 3, right? There is no other factorization for 3. So therefore, the larger integer here must be 3. So you have 2y plus 2x plus 1 is equal to 3. And 2y minus 2x minus 1 should be 1, right? And from this, if you solve, you will get y should be 1 and x should be 0, right? You can see, solve these equations and you will realize that y should be 1 and x should be 0. But that is a contradiction because we said that we wanted positive integer solutions for x and y, whereas here x is coming as 0, which is not positive. So therefore, we have achieved a contradiction, and therefore the equation does not have positive integer solutions for x and y, right? So here, the main idea of factorization method was what? We converted the original equation into several equations that are easier to deal with. For example, here the original quadratic equation became a linear pair of linear equations. And those linear equations are easier to deal with, and you can use properties of integers to try to get a contradiction. So that was the idea here. Sometimes you achieve factorization in a slightly different way. So for example, if you have a question like this, question 2, here the question is, let k be a positive integer and k is greater than equal to 2. K is greater than equal to 2. We have to now prove that x into x plus 1 is equal to y power k has no positive integer solutions. Has no positive integer solutions. Okay. Before we go into this problem, I will be doing a sub problem, or I'm going to make a claim and I'm going to prove my claim, and then we'll use that claim while solving this problem. So what is the claim? Let AB be the product of two positive integers a and b. Two positive integers a and b. And let AB be equal to the kth power of an integer, where k is greater than or equal to 2, right? We are saying if A and B are co-prime, their GCD is 1, then both A and B are also kth powers of some integers. That is the claim. If A and B are co-prime and the product of A and B is the kth power of an integer, then both A and B will be the kth powers of some integer. So more concretely, the question says that if AB is equal to x power k, prove that it implies that A is the GCD of A and x power k, and B is the GCD of B and x power k if A and B are co-prime. So this is the claim that I first want to prove. Okay. So we'll be using that later. So let's try and see this. Let AB is equal to x power k and x is greater than 0, right? Since A and B are co-prime, we know that A power k minus 1 and B will also have GCD 1, right? Correct. And we have properties of GCD. Some couple of properties of GCD that we know are these. Let A and B be co-prime and M and N are any two positive integers. It is obvious that A power M and B power N will also be co-prime, right? Also, you can also show that for any positive integers, A power N and B power N will be equal to A and B power N. This is for A and B being co-prime. If you have A power N and B power N's GCD is supposed to be found, it will be just the nth power of the GCD of A and B. If A and B are co-prime. These are properties of GCD, right? So from here and using these properties, we'll make our proof. So let's do that. Suppose AX GCD be equal to D, right? Therefore, A power k and x power k's GCD should be equal to D power k, right? This is a property of GCD. If A and x GCD is D, A power k and x power k's GCD will be D power k. However, this means that A power k is the same, but we know x power k is AB, right? So x power k is equal to AB. The GCD of this is supposed to be D power k now, right? Now, the GCD of this is going to be, you can take A common outside. It is the GCD of A power k minus 1 and B is equal to D power k, right? So now we know that A power k minus 1 and B's GCD is 1. So therefore, A is equal to D power k we are getting, right? And what is D power k? Basically, we have proved that A is equal to GCD of A and X power k. We have just completed our proof. So A becomes the kth power of a number. What is that number? It is the GCD of A and X, where X power k was equal to AB, right? Similarly, you can also show that B is equal to B and X GCD power k, right? So now we have established our claim that if two numbers are co-prime and the product of those numbers is a power of some integer, AB is equal to X power k, then A itself is A and X GCD power k, and B is the GCD of B and X power k, right? So now let's get back to our original problem. We had to prove that there are no positive integer solutions of this equation, right? So here, let's assume we have x and x plus 1. x and x plus 1 are co-prime to each other, co-prime to each other. That is obvious. And we have product of these two co-prime numbers is a power, kth power of some integer, right? So that implies from our claim that x and x plus 1 are also kth powers of integers, right? Kth powers of integers. So we can assume now that x should be some u power k and x plus 1 should be some v power k, because we know that x and x plus 1 are both kth powers of some integers. And let's, looking at the equation, now we are getting u power k, v power k is equal to y power k. So therefore y must be equal to uv, right? Here u and v are positive integers. So if you try to calculate now v power k minus u power k, that is basically x plus 1 minus x, so which is 1. And that can be factorized like this: v minus u, v power k minus 1 u plus v power k minus 2 u square, and so on till u power k minus 1, right? So now what we are getting is 1 is equal to product of two different integers, right? 1 can never be written as a product of two different integers. These are different integers. So we have gotten a contradiction. We have achieved a contradiction here, because according to our claim, both x and x plus 1 are powers of integers. And now looking at this equation, we are getting 1 is equal to the product of two different integers. So that means that this does not admit any solutions in positive integers, because if it does, we are arriving at this contradiction. So notice the claim that we have proved earlier and how we are using that claim in order to prove the original question. Okay, let's move on to the next idea. Now we look at equations that we'll solve using the congruence method. This is question 3. We have to prove that the equation x square plus y square minus 4z square equal to 7 has no integer solutions. Has no integer solutions. So what is the congruence method? In the congruence method, the key idea is to select the right modulo with which we need to take the equation congruent to. So we are going to take mod of some number on both sides of this equation and try to figure out whether it makes sense or not, or whether we can come to a contradiction or not. So we know if integers x, y, and z satisfy this equation, then we know from a previous problem that x square, y square, z square can all be only 0 or 1 mod 4, right? We know that square of any integer must be either 0 mod 4 or 1 mod 4. That was the first question that we discussed in today's session, right? So once we know that, we can basically take mod 4 on this side and mod 4 on the RHS also, right? If you take LHS mod 4, we know that this is 0 mod 4 because 4 is multiplied with it. So the only possibilities here are 0, 1, or 2 mod 4. Why am I getting only 3 possibilities on the left hand side? Because x square can be 0 or 1, y square can be 0 or 1, and this is guaranteed to be 0 mod 4. So obviously it could be 0, 0, then you get a 0, 0 and 1, you get a 1, and 1 and 1, you get a 2 mod 4. These are the 3 possibilities when you take modulo 4 on the left hand side. And on the RHS side, RHS mod 4 is 7. So 7 is simply 3 mod 4, right? So what we are getting is a direct contradiction, because the left hand side can never be equal to 3 mod 4. So that means that there are no integers x, y, z that can satisfy this equation, right? So that is the proof by congruence method. Mostly in congruence method, we arrive at a proof by contradiction. We show that it is not possible to get a particular situation. Let's look at a more complicated question. This is question number 4. We have to find all positive integer solutions m n x to the equation 2 power m plus 3 power n equal to x square. Okay, so correct. From by looking at the equation itself, you can realize that 3 does not divide x. Why? If 3 divides x, think about it. This is 0 mod 3, this is 0 mod 3, but this is not 0 mod 3, right? You will get a contradiction because this will be either 2 or 1 mod 3 plus 0 mod 3 should not be equal to 0 mod 3. So it is obvious by looking at the question itself that 3 doesn't divide x. So that implies that x square has to be 1 mod 3. Why? Because if 3 doesn't divide x, then x can only be either 3k plus 1 or 3k plus 2, right? In both the cases, when you square it, you will get that x square will become 1 mod 3. You can check that yourself. In both the cases, either 3k plus 1 or 3k plus 2, you'll get x square is 1 mod 3, right? Okay, so now if you take mod 3 on both sides of the equation, take mod 3 both sides. Correct. So what we get here is 1 on the RHS side. 1 is congruent to 2 power m plus 3 power n mod 3. So 3 power n mod 3 is simply 0, right? This is not going to give us anything. 3 power n mod 3 is 0 mod 3. So we have 2 power m mod 3 should be 1, right? And 2 power m mod 3 can be multiple things, depends on the m. So for example, 2 power 1 is 2 mod 3 and 2 power 2 is 1 mod 3, right? So think about it. 2 power 3 is 8, which is 2 mod 3 again, right? Can it ever be 2 mod 3? If you get a 2 mod 3 here and a 0 mod 3 here, you will never be able to equate it to 1 mod 3, right? But if you get a 1 mod 3 from 2 power m, then that means 1 mod 3 plus 0 mod 3 will satisfy this equation, right? So when do you get a 1 mod 3? When you do 2 power 4, you get 16, which is also 1 mod 3. So you should see this pattern here that 1 mod 3 will come in powers of 2 only if m is even. So from here, it follows that if the equation has to be true, m must be even, right? Only if m is even will you be able to satisfy this equation modulus 3. So what we'll do now is take m is equal to 2k since it is even, right? You get 2 power 2k plus 3 power n is equal to x square. And now we can factorize this a little bit. X square minus 2 power 2k is equal to 3 power n. And we can write it as x minus 2 power k, x plus 2 power k is equal to 3 power n, right? And we know already that 3 does not divide x, right? Correct. So from here, uh, x minus 2 power k and x plus 2 power k is equal to 3 power n. So the sum of these numbers, x minus 2 power k plus x plus 2 power k, is equal to 2x. And since 3 does not divide x, it implies 3 does not divide 2x also. So the sum of these numbers is not divisible by 3, right? Sum of these numbers is not divisible by 3. So How will we get this equality? Uh, so each of these individual numbers must not be divisible by 3, I think. Or at one of them can be divisible by 3, but the other one can't be. Uh, let's think about this. So we have both the integers x minus 2 power k and x plus 2 power k are powers of 3. Okay, now we get it. The left hand side number is 3 power n. So the only prime factor here is 3, right? Standard factorization of this is 3 power n. So this side also you can get only 3 powers, right? Powers of 3 they have to be. They cannot be powers of 2 and all, because then you cannot be equal to 3 power n. So both these integers are powers of 3, but the sum of these integers is not divisible by 3. How is that possible? It is not possible if you have 3 power 1 and 3 power n minus 1 and stuff like that. It's not possible if this number is divisible by 3 and this number is also divisible by 3, then the combination should be divisible by 3, right? The only way it is possible that both the integers are powers of 3, but their sum is not divisible by 3, is if one of them is 3 power 0 and the other one is 3 power n, right? Only then 3 power 0 is 1. So the sum of these two integers will not be divisible by 3, right? So therefore, this argument convinces us that x minus 2 power k must be 1, which is 3 power 0, and x plus 2 power k must be 3 power n. I hope you got the argument. The product of these numbers is 3 power n, so both of them must be powers of 3. The sum of these numbers is 2x, but 2x is not divisible by 3, because x is not divisible by 3, right? So how can that happen? The only way for it to happen is one of them powers to be 3 power 0 and the other power is 3 power n. So using this, now we can simply solve, and what we can do is you can eliminate x from these equations by subtracting this minus this. You will get 2 power k plus 1 is equal to 3 power n minus 1. This is the equation that we get after eliminating x from here. Right. So let's work on that now. We have 2 power k plus 1 is equal to 3 power n minus 1. If n is odd, then 3 power 2k plus 1 is equal to 3 into 3 power 2k. And that should be equal to some 2 power k plus 1, right? Now here, if you take, this is what? This is 3 times the square of 3 power k, right? This is 3 into 3 power k square. So square will always be 0 or 1 mod 4. We know that. A square number is always 0 or 1 mod 4. So if you take mod 4, the whole number here should either be 0 or 3 mod 4, right? On the other side, 2 power k plus 1 will either be, if it is k plus 1 is even, then you will get 0 mod 4, right? But if k plus 1 is odd, right? But k plus 1, one second, let me think. Uh, we had what? We had this equation. We are saying 3 power n itself is 0 or 3 mod 4, right? So correct. So 3 power, if n is odd, if n is odd, okay, let's just take some examples. If n is odd, it can be 3 power 1 minus 3 power 1 minus 1, or 3 power 3 minus 1, or 3 power 5 minus 1, and so on. 3 power 1 minus 1 is coming out to be 2 mod 4. This is coming out to be 9, 27 minus 1, 26. This is also 2 mod 4, right? And notice that this is 3 power 5, 243, minus 1, 242. This is also 2 mod 4. Okay. So we are always getting 3 power n minus 1 is equal to 2 mod 4 if n is odd, right? Uh, the left hand side, 2 power k plus 1, k was odd. Earlier we had said m is equal to 2k earlier, if you remember. K was odd number. So k plus 1 is even. K plus 1 is even means 2 power k plus 1 is 0 mod 4. So earlier, if you remember, what was k? K was an odd number because we had taken m is equal to 2k earlier, where 2 m was an even number, right? We had taken that. So k is an odd number. Therefore, k plus 1 is even number. So 2 power k plus 1 is basically 0 mod 4. And 3 power n minus 1 will become 2 mod 4 if n is odd. So that implies that n cannot be odd. So n must be even. We have now n is even. So n is equal to 2l, right? And now we have this equation 3 power n minus 1 is equal to 2 power k plus 1 becomes now 3 power 2l minus 1 is equal to 2 power k plus 1, right? And now L here is odd. L is odd and we know K is also odd. These things we know. And we try to solve this equation by doing it like this. It is 3 power L plus 1 and 3 power L minus 1 is equal to 2 power K plus 1, right? Now, the number L is odd. 3 power L is also odd. So we can write 3 power L as 2u plus 1. So 3 power L minus 1 will be 2u. So this side will become 2u plus 1 into 2u is equal to 2 power k plus 1, right? So we have basically 4 2u plus 1 plus 1. So 2u plus 2 here, if you think about it. L 3 power L was 2u plus 1. So 3 power L plus 1 is 2u plus 2. So you take 4 common here, it is u into u plus 1 is equal to 2 power k plus 1. You simplify this, you will get u into u plus 1 is 2 power k minus 1, right? Okay. So if u into u plus 1 is 2 power k minus 1, if u is greater than 1, at least one of u and u plus 1 has an odd prime factor. If u is greater than 1, u can be 2 or u can be 3. So if you take u is 2, 2 into 3, you can see that 3 has an odd prime factor, which is 3. If you take any higher number for u, maybe 5, 5 and 6. Clearly 5 is an odd prime factor. So at least one of u and u plus 1 has an odd prime factor. But the right hand side, 2 2 power k minus 1 has no odd prime factor. So that is a contradiction. So that means u must be 1. And if u is 1, now we start getting our values. If u is 1, you get 1 into 2 is 2 power k minus 1. So that is k must be 2 then. And if you get k is equal to 2, then you get 3 power L, 3 power 2L minus 1 was equal to 2 power k plus 1. And k is 2, so 2 power 3, this is 8 plus 1, 9. So 3 power 2L is equal to 9. So L is equal to 1. You get L is 1, you get N is 2, and you will finally get M is 4 and X is 5. If you go back and work through the steps that we have come to reach here, you will realize that the ordered pair that satisfies M and X is 4, 2, and 5. We have finally gotten K value. K value gave us M value. Once you got M value, we can put that in the original equation, we get N also, right? So this is our solution. Notice at several stages, we did modulo 3 and modulo 4. And modulo 3 and modulo 4 helped us reduce the cases and think about it in a more, in a different way, in a concrete way, right? Let's look at another question. This is the estimation method I will show you. So this is find all integer solutions. Integer solutions to 5x squared minus 6xy plus 7y squared is equal to 130. So suppose this equation has integer solutions. Equation has integer solutions. So the idea here is if it has integer solutions, that implies that it must have real number solutions, obviously. Real solutions, right? And if it has real solutions, I can think of writing this quadratic as a quadratic in X and taking a condition on its discriminant, right? So if you think about it, it is a quadratic in X like this. And since it has real solutions, we can say discriminant is greater than or equal to 0. And that gives us 36y square minus 4 into 5 into 7y square minus 130 is greater than or equal to 0. And from here, you will be able to deduce that 104y square is less than or equal to 2600, which will give us y square is less than or equal to 25. So mod y will be less than or equal to 5. And y can take what values? Minus plus 5, plus minus 4, and so on, plus minus 1 and 0. These are the possible values of y that you will get. How are we getting it? We said that since integer solutions are possible, there must be real number solutions. And if real number solutions are there, this is a quadratic type of equation, so we can write a condition on the discriminant. And from there, we get an inequality on y. So once we have an inequality or a bound on y, we can now just check different values of y, put it in the original equation, and you can deduce easily that the only solutions are 3 and 5 and minus 3 and minus 5 for x and y. These are the only two values that will satisfy the equation. So that is another way to basically decide how many solutions are there, because we got an estimate on y based on our discriminant condition. Now, what we will see are some special indeterminate equations. Special indeterminate equations and how solutions for those are constructed. So the first one that we will see is the equation called this one, x square minus dy square equal to c. Here d and c are integers. D and c are integers. D is greater than 0. D is not a square number, and c is not equal to 0. Okay. This is the more general equation. A special form of this equation is when you write x square minus d square equal to 1. And this equation is known as Pell's equation. Pell's equation. Now, we are not going to get into the proof of Pell's equation, which is a deeper subject. But what I will tell you are some key facts that will help you solve equations like this. So we can prove that this second equation, this is the first equation, this is the second equation. The second equation must have an infinite number of positive integer solutions. Infinite number of positive integer solutions. And there is a way to construct a new solution if you have found one solution. So the second equation has an infinite number of positive integer solutions, the Pell's equation. And once you have a basic solution, you can find a basic solution to this equation by trial and error. If you find a trial and error solution, x1, y1, you can construct any number of solutions for this equation by using the following recurrence. So our equation is this. This is the second equation, x square minus dy square equal to 1. And let's say we have a solution x1, y1 is the solution that you have found. And you may find it by trial and error. How do we construct any other solution? Xn can be written as 1 by 2 x1 plus root d y1 power n plus x1 minus root d y1 power n. And similarly, yn will be 1 by 2 root d, and this is x1 plus root d y1 power n minus x1 minus root d y1 power n. I should remove these unnecessary parentheses. Root d y1 power n. So this is how you construct a new solution. Okay. Here n is an integer. And basically the recurrence that the solutions follow is this. Xn is equal to 2x1 x of n minus 1 minus x of n minus 2. And yn is equal to 2y1 2 y1 y of n minus 1 minus y of n minus 2. So this recurrence has these solutions. And basically using the one primary solution that you have found, which can be found by trial and error, you can construct more solutions to it. So the Pell's equation has infinite solutions. You just need to find one of them, and then you can find many more, right? Also, the original equation, the first equation, does not always have a solution. So what was the first equation? X square minus dy square is equal to c. This equation may not always have a solution, but if it has a solution, there are infinite of them. There are an infinite set. There are infinite solutions. So the other equation, the exact Pell's equation, this always has an infinite number of solutions. All you need to do is find one of them, and then you can use the recurrence or the formula that I showed you earlier to construct many more solutions for this, right? So I'm not going to go into too much detail of this equation. Pell's equation is a course in higher maths. So it is quite advanced theory. We are not going to worry about how the proofs have come, but we are just listing down some results that might be useful for us. The next type of indeterminate equations that you might have seen are the Pythagoras theorem equation. X square plus y square is equal to z square, this equation, right? So here I'll just state a theorem. This is a very standard theorem. The proof of this is in there in many places. You can find it online. So what we will say here is assume that y is even. All positive integer solutions x, y, z of x square plus y square equal to z square, satisfying the condition that x and y are co-prime and 2 divides y. Y is even and x and y are co-prime, right? Can be written as this: x is equal to a square minus b square, y is equal to 2ab, and z is equal to a square plus b square, where a and b are any integers satisfying a is greater than b greater than 0, one of a and b is even and the other one is odd, and a and b are co-prime, a and b GCD is 1. So the Pythagoras theorem admits infinite solutions, and the solutions are always in this form: x is a square minus b square, y is 2ab, z is a square plus b square, where x and y are integers which are co-prime to each other and y is the even one. And what about a and b? The a and b integers are such that a is bigger than b. One of a and b has to be even, the other one has to be odd, and a and b have to be co-prime to each other, right? And the last kind of irreducible equation that you might sometimes see is the equation of this form: xy is equal to zt. Here there are four unknowns, and all positive integer solutions you have to find. And this is actually pretty easy to find. So we can say let x and z GCD be a, then x should be a times c and z should be a times d, where c and d are co-prime with each other, right? Hence, if you put x in this equation, ac y is equal to z is ad t, right? So from here we are getting cy is equal to dt. And because we know that c and d are co-prime, therefore c and d don't have any common factor, and this side is divisible by d, so this side also should be divisible by d. So d should divide cy, which implies d divides y, right? So if d divides y, you can assume y to be bd, and if you put y is equal to bd here, you'll get c into bd is equal to dt, so t will become dc, right? So finally you are getting what? You're getting x is ac, y is bd, z is ad, and t is bc. These are the four basic solutions for in positive integers for this equation. Here, obviously, a, b, c, d are all positive integers. And CD, GCD is 1. C and D are co-prime numbers. So X and Z are basically AC and AD. Y and T are BD and BC, right? Now, using this solution, we can basically try and solve a couple more questions. So for example, the first question that I want to look at is this one, question number 6. So let ABCD be all positive integers such that AB is equal to CD. We have to prove that A power 4 plus B power 4 plus C power 4 plus D power 4 is not a prime. So now think about it. We just now saw how we solve an equation in positive integers of this form, right? AB is equal to CD. We saw how to solve this equation. We saw that A can be taken as some US and C will be some VS, and B can be written as VT and D will be some UT, right? Basically, another way to think about it is by saying if your equation was xy is equal to zt, you can rewrite this equation as x by z is equal to t by y, right? And you can say that if x by z and t by y are some irreducible fraction c by d, so from here you can say since x by z is c by d, x becomes ac and z becomes ad, right? Correct. And from t by y is c by d, you can say t becomes bc and y becomes bd, right? So similarly here, you can say a by c is equal to d by b. So you can say a by c is equal to d by b is equal to u by v, let's say. U and v are irreducible. So GCD of u and v is 1, right? So then a can be written as us, c can be written as vs, where s is some positive integer. Similarly, d can be written as ut and b can be written as vt, right? That is how we are getting the solutions us, vs, vt, ut for a, b, c, d, right? Once you get these solutions where u, v, st are integers and the gcd of u and v is 1, then we can try and think about what is this, right? A power 4 plus b power 4 plus c power 4 plus d power 4 can be written as u power 4 s power 4 plus v power 4 t power 4 plus v power 4 s power 4 plus u power 4 t power 4. And from here we can take common u power 4, you get s power 4 plus t power 4, and then v power 4, and you get s power 4 plus t power 4. And we are able to show that it is u power 4 plus v power 4 multiplied by s power 4 plus t power 4, which is a product of two positive integers. Product of two positive integers. So therefore, if the number a power 4 plus b power 4 plus c power 4 plus d power 4 has been expressed as the product of two positive integers, it cannot be prime. So that concludes our proof. Here, what are we using? We are using the solution of the indeterminate equation xy is equal to zt. And that solution helps us to solve this problem. Let's do another question. This is prove that the equation n plus 1 by 2 is equal to k square has an infinite number of positive integer solutions. Infinite number of positive integer solutions. So let's think about this equation. We'll simplify it like this: n square plus n is equal to 2k square. And if I multiply by 4, you'll get 4n square plus 4n is equal to 8k square. And I just need a plus 1 here. I'll say 2n plus 1 square should be equal to 8k square plus 1, right? Now I can rewrite this like this: 2n plus 1 square minus 8k square is equal to 1, right? Now think about it. Our form, our Pell's equation was x square minus dy square equal to 1, right? We had discussed that this Pell's equation has infinite number of solutions, right? So here you can write it as 2n plus 1 whole square minus 2 times 4k square or 2k whole square, right? Equal to 1, right? So here we are getting x is this, y is this, and you are getting the equation x square minus 2y square is equal to 1. X is 2n plus 1 and y is 2k, right? So this equation x square minus 2y square equal to 1 has an infinite number of solutions because it is in the form of Pell's equation, right? Why did we take 2 here? Because we knew that in Pell's equation, D must not be a perfect square. D must not be perfect square. right? So we have set it up in a form where it is in the Pell's equation form. And now we can say that X is odd, Y is even, and this equation we can find some standard solution x1, y1 and construct a lot more solutions using the recurrence relation that we had seen earlier. And finally, once you get a solution, we can get the solution for the original equation by saying n is equal to x minus 1 by 2 and k is equal to y by 2. Solve this standard Pell's equation, find the infinite solutions here, and then convert each solution to the corresponding n and k solution of this one, right? So the theory that we are using here is the theory of the Pell's equation and the fact that that equation admits an infinite number of solutions. So you will see applications of these methods in several problems in the future. I will be sharing an assignment with more questions. You should try those out. Those will help you apply the things that we have learned in today's session. So that's about it for this section of the course. The next video will also be a video on problems in number theory. We'll do a few more advanced problems and we'll revise the concepts that we have learned so far. I'll see you in the next one.